So before I get to talk about enzymes and exergonic and endergonic reactions, I need to talk about energy. So let's go back in time here for 1 second. So first, let's try to define what energy is. Energy can be loosely defined as the ability to do work. Any organism or entity that can that allows something to do work is something that is providing energy. Now, there are essentially two states of energy. The first one of them is said to be the kinetic state, or motion energy. Kinetic means movement. So this is the energy that it's created as movement is created. The other part, like a name of energy, the other state of energy is known as the potential energy. And this is the energy that gets stored after some sort of movement is produced. Now, to exemplify that, usually people use this following representation here. You think about a bike at the bottom of the hill. That bike, if it wants to go up the hill, it needs some sort of kinetic energy. So let's bring that bike up the hill now, and then if as that bike gets to the top of the hill, this kinetic energy is transformed, and is transformed into potential energy. Because energy is never necessarily created. I mean, the person that provided the energy for that bike, like to go up the hill, somehow harvested that energy from a vegetable for an animal that he ate, and that plant that the person ate actually had some stored potential energy because it harvested energy from the sun. It's never created. But anyway, let's go back to our bike example here. Now that you are on top of that hill, you have potential energy, and then if you want to go down the hill, you're just going to use this potential energy to create more kinetic energy as you get to the bottom of the hill. So, very simple example showing like these two states of energy. All right, instead of trying to illustrate chemical reactions here, to show what enzymatic activity looks like, I'm going to use an analogy here. Let's think about a pile of bricks. I'm going to draw really fast here, and this pile of bricks is found in its disassembled state. It's just a pile, it's completely disorganized, and then if you want to move this pile of bricks to a more organized state, you're going to have some sort of energy input. And then with this energy input, you can create something that is known as a brick wall, right? So this is going to be the equivalent of my chemical reaction here. Now, my pile of bricks, it's the reactant of this chemical reaction, and as it moves to the brick wall state, it becomes the product of that chemical reaction. So the blue arrow here indicates the direction of the chemical reaction. So let's imagine now what is going to be happening in this chemical reaction here. As on this graph here, on the x-axis you have the progress of the reaction, and then on the y-axis you have the molecule's potential energy. I'm using, like, of course we're talking about bricks here, but like imagine if this was actually if that was you assembling a bunch of carbon molecules into a carbon chain, it would be essentially the same thing. When you are combining chemical elements, you are increasing their potential energy in many cases. So what is interesting though is that in this case here, you are actually going from a state that has a very, very low potential energy in the beginning to a state, like, because this is where the reactants are, to a state where you have like lots of stored energy, lots of potential energy. And you can actually start labeling like things in this graph here, and you can actually like see that like that in the beginning, even though those molecules were disassembled or the pile of bricks was completely chaotic, you still have some energy stored in these reactants. I mean, that's like the bricks have some sort of energy that can provide the resistance that, or the energy that it's stored in the brick wall. Now, the other thing that you see here is that the energy stored in the products is a lot higher. But what that tells you though is that like if you want to go from a state like from lower potential energy to a state of higher potential energy, you need to provide energy. And this energy that gets provided to the system is known as the activation energy. So on this reaction here, energy input is necessary for the chemical reaction to occur. Because of that, this reaction is said to be endergonic. Endergonic reactions are those that require an energy input, and that in which the products also have a higher energy than the reactants. Now, let's imagine now the opposite of this. Let's imagine now that we're going from the reactants state to the products, but in this case now you're starting with the brick wall and you're moving to the pile of bricks. Well, you imagine that this is a lot easier to do, and because you actually start with the reactants that have like a lot of potential energy, and it's very easy to move to the product that has a lower potential energy. So again, you can label like things here. So the reactants have their energy stored in them, and this energy stored is much higher than the energy stored in the products. And one thing that is interesting about this fake chemical reaction here is that the activation energy necessary for the reaction to take place is much lower than in the previous graph. So this reaction, because you're moving from reactants that have higher energy to products that have lower energy, this reaction is said to be to release energy. So this energy gets released. You need a little bit of activation energy, but overall you actually release energy through this chemical reaction. And then we call this an exergonic reaction. Those reactions are said to be spontaneous because over time any brick wall comes down to a pile of bricks. If you leave it long enough, this brick wall eventually, just by chance, will end up like becoming a pile of bricks. Molecules that are really long and really well elaborated, arranged like bricks in a brick wall, eventually will collapse at some point. Now, so you say that this is a spontaneous reaction that inevitably will occur, but that doesn't mean that it's an instantaneous reaction. So and what prevents these reactions from being instantaneous is this demand for an activation energy. So, but as soon as this activation energy is provided, the reaction will take place. Now, following with my example here, let's try to understand a little bit more about this activation energy. There are certain molecules that can reduce this activation energy. So this molecule that can be added to the reaction, it's said to be a catalyst, and its main property is to reduce the activation energy or making it easier for the reactions to take place. A good example of catalysts are enzymes. Enzymes can facilitate chemical reactions by lowering the activation energy and making them easier to occur. So again, I'll go back to my example of the brick wall. So I'm going to move from the brick wall to the pile of bricks. And what creates the activation energy for this brick wall to go to the pile of bricks could be any force. So in this case here, I'm using the example of wind. Now, if I were to be a catalyst, if I were to be an enzyme on this chemical reaction, what I would do, I would start pushing this wall in a way that can assist the wind. So in that case here, I am an enzyme assisting the wind. Of course, I would have to be really strong, to actually provide some sort of energy that would assist the wind, depending on how thick the mortar is in this brick wall. But essentially, I could assist the chemical reaction, reduce the activation energy. Now, I'm using here the example for an exergonic reaction, but I think it's important to remind you guys that catalysts, enzymes, can occur both in exergonic and endergonic reactions. Now, when enzymes are actually acting, they're increasing the rate of the reaction, but they're not increasing the amount of product that is being formed. In the end, if I am the enzyme here, I'm not adding more bricks to the pile in the very end. I'm just making sure that all the bricks that were there to begin with end up in the pile of bricks, but I do not create more bricks. So let's use like a real example of that. So let's think about this chemical reaction here, in which you're combining carbon dioxide and water and transforming that into this molecule known as carbonic acid. Without an enzyme, this reaction occurs at a pace of 200 molecules per hour, without the enzyme. But if you add this enzyme known as carbonic anhydrase, you increase the pace here quite a bit. So in the presence of carbonic anhydrase, the reaction will occur at a speed of 600,000 molecules per second. But again, you're not creating more products, you're just increasing the rate. If you don't have carbon dioxide and water to conduct this reaction, you simply will not form 600,000 molecules. You need 600,000 molecules of carbon dioxide to form 600,000 molecules of carbonic acid. All right, so, but how does that occur? Well, it's not magic here. The enzyme's ability to reduce the activation energy has to do with the structure of the enzyme. So let's see an example here. And in order to talk about this structure of enzymes, I need to talk about this key and lock model. So I imagine here two substrates, two reactants that will interact with an enzyme. The enzyme is represented at the top here, and this enzyme can actually get these two substrates and combine them. And one thing that is very interesting here is that if you look at the shape of the enzyme, right here, it corresponds to the shape of, or roughly corresponds to the shape of the substrates. All right. And one thing that is very interesting is that as these substrates plug themselves with the enzyme goes through a little bit of a conformational change. They change the shape a little bit. So this small change in the structure of the enzyme is known as the induced fit. And what the induced fit does, it can actually add stress to the chemical bonds of the two substrates in a way you can combine them or break them apart. So the structure of the enzyme through the induced fit mechanism can add strength to the chemical bonds and allow you to essentially transform these two substrates into a new product. So it's a very simple mechanism. It's not necessarily magic. It's just, well, it just has to do with the structure of that enzyme. Now, this key and lock model, of course, determines that there's a specificity. And one thing that is very interesting about the key and lock model as well is that even though the enzyme can actually accommodate the shape of the substrates, the enzyme on the very end remains unaltered. If you go compare this picture here, the enzyme in the beginning of the reaction looks essentially the same at the end of the reaction. So the enzyme does not necessarily take part on the reaction. It assists the reaction, but it's not one of the reactants. It's not becoming a product. Now, I think this actually summarizes quite well the function of enzymes, and I hope that this is going to be helpful for you in understanding